Hello, good morning, good afternoon, good evening, and welcome to this YouTube livecast. My name is Houman Zarrinkoub. I am the Principal Product Manager for the wireless communication products at MathWorks. And today I'm joined by my friend Uvaraj. Go ahead, Uvaraj, introduce yourself, if you don't mind.
Hello, everyone. Nice to meet you all here. I'm Yuvraj Natarajan, and I'm from the application engineering group in MathWorks. And my primary focus area is on the wireless communication related technologies like the 5G, LTE, WLAN, Bluetooth, satellite communication, and so on. So nice to have you all here and hope you enjoy.
Thanks. Yeah, today's talk is about the title, as you can see here, what is ORAN and how to implement it. We're going to do a little overview of the Open Radio Access Network and the practical aspects of implementing it. Just to give you a little bit of my background, I did my bachelor, master, and Ph.D. in Canada. I went to McGill University in electrical engineering, and I did my master and Ph.D. at University of Quebec, Institut National de Recherche Scientifique, on telecommunication. I worked at one of the best companies in Canada, Nortel Networks at that time, and then joined 21 years ago to MathWorks as development manager, and further on product manager for many signal processing and wireless communication products. Uvaraj, tell us about your background.
That's great to hear about your background and really impressive, Houman. So I've worked in a few companies before MathWorks. So I'm here in MathWorks in application engineering group, and before which I have been working with Cisco systems on the SON R&D as well as the protocol stack R&D, and I've also worked on various other technologies R&D part like the LTE and again from physical layer to various layers across the protocol stack. I've also worked as a research assistant in the Center for Communication System Research in UK, and I did my master's in the University of Surrey in UK and my bachelor's in electronics and communications. That's all about me. Yeah.
That's great, Uvaraj.
So maybe let's quickly get started, Houman. Can you explain us about what is ORAN and some background behind that?
So ORAN, in terms of terminology, it stands for Open Radio Access Network. So as you can imagine, in the wireless communication, there's a core network that regulates traffic across the internet, wireless traffic. And then there is an area that is at the node of the wireless network connecting to end users, our phones, our laptops, and so on, where the base station, or otherwise these days known as G node B, is essentially communicating with your devices, with the user equipment. Now, the radio access network is all about the control of the access to the network. And traditionally, the design of these radio access networks have been hardware-centric. So the elements that compose the radio access network were essentially physically connected to the G node B, or the base station in this case. So the traditional way, you have a dichotomy of the RF component, all the antenna and all the RF equipment, and the baseband unit, right? And that's what you see on the left-hand side of the picture. And usually, if a operator, somebody who gives you and me service for cellular connectivity, they would acquire both the baseband unit and the radio unit from the same vendor, right? So that's the traditional hardware-centric way. Now, Open Radio Access Network tries to modularize this, tries to say, okay, radio access network can be viewed as multiple components, and each of these multiple components can have the ability to communicate with each other, and more importantly, can be provided by different vendors. So this is the essential motivation of Open Radio Access Network. From core network all the way to connectivity through RF to the mobile, you take that radio access network and you subdivide it into elements. And each element enables interoperability between these multiple components, right? And as you can see on the right-hand side, this is characterized by 3 components. And we're going to discuss all the OCU and ODU and ORU in detail. And between them are defined interfaces. So that's the story and motivation behind Open RAN.
Great.
Now, let me ask you a question. Who is the standard body responsible for the Open RAN?
Yeah, the Open RAN is basically, formulated and maintained by the ORAN Alliance. So it's actually a group of organizations who have come together, operators, vendors, equipment manufacturers, coming together and forming a forum called Open RAN Alliance. And this was, basically formed in the year of 2018. It's a group of people who formed the XRAN and the CRAN alliances earlier. So merged into ORAN, and that grew. And in 2020, the ORAN Alliance grown further, and it started working on the specification work, on the policy work, defining the standards as such, the interfaces as such. And we can broadly classify the work done by the ORAN Alliance into 3 different mainstreams. So one is on the standardization efforts, so where they define various components of the ORAN architecture as such, as you see in the figure here. So we have the CU, DU, and RU, which helps in taking the user data and the control information. You also have the other nodes like the RAN intelligent controller, which is again split into near real time and non-real time. And again, various interfaces connecting that with the real ORAN interfaces or the components, and connecting to the core network and the communication between them. All those are defined. There is also other mainstream which works on the testing and standardizing part of it. The conformance testing, like the interoperability between these nodes are well defined there. And the third one is again on the software community. So the ORAN software community works on building reference applications, which is good for anyone to kickstart with the ORAN development as such. So these are the mainstreams about the alliance and the history behind that. And again, MathWorks is a part of ORAN Alliance from 2021.
That's great.
So maybe Houman, can you please explain us or take us through what are the various aspects which are covered by the standard as such?
Yes, so this picture kind of gives you the overall architecture of these componentization that I talked to you about. So what components are defined in the Open RAN specification? From left to right, you see that we start from the Open Radio Unit, known as ORU. And this radio unit is essentially involved with the radio communication, right? And then the previously known baseband unit that was near but not necessarily on the G-Node B tower in the previous modes of industry is decomposed into 2 components. You have the distributed unit, or ODU, and the centralized unit. OCU, right? And then the combined traffic and data that on the is acquired from that is transmitted to core network. So these are the essential functional units of the ORAN standard. And I want to stress the significance of these interfaces, right? So if you want to achieve modularity and each unit be provided by a different vendor, you need to have a standard interface so that the data written by one vendor is exactly readable and actionable by other vendor. That's the meaning of necessity for defining those interfaces. So the major challenge of this kind of architectural subdivision is making sure the interfaces between the radio unit, distribute unit, and the centralized unit are well defined, and different vendors can talk through that interface and make everything work. Now, Waraj, I wonder if you can tell me about these significance of these interfaces a little further. The front hall, the mid hall, the back hall. Tell us more about the job of those guys.
Yes, so basically, the front hall is something which is, connecting the radio head or, towards the base station to the DU part of it. And that's where high-speed IQ data transfer takes place. And there is a separate interface which is specifically designed to take care of, the high-speed data transfer. But the mid-hall is something which is actually connecting the DU and the CU, and that's taking different splits. So there are various ways in which we can, bisect the protocol stack to make the mid-haul happen. And basically, this can be moved to a cloud-based unit, so edge cloud of the complete network. So this makes the operator, easy to deploy those aspects which are software-based and which can be easily deployed in a Docker and a containerized, environment of the system. And backhaul is something which is something which we connect to the cloud network. Again, there are various protocols defined, for the communication between the backhaul. And if it's more into the cloud, we normally use the HTTP-based JSON and API-based communication for the communication between the networks.
That's great. Also, Waraj, I want you to now connect all these different interfaces with different layers of the OSI model and different splits or options. You have done some research on that, right? So tell us more about the ORAN splits, please.
So that's a very interesting part of the ORAN architecture as such. So if you see, you can bisect the protocol stack itself in various location of the stack. So the data, the user data and the control data, which comes basically from the core network. So the RRC takes care of the control information, and SDAP takes care of the user data. And then if you have a split between the PDCP and the higher layer to that, we can consider that as an option 1 for the split. Likewise, we have various options where you can bisect, the protocol stack in order to create a logical split between, the DU and the CU. So we have various other options like option 2, 4, 6, cutting the layers as such from PDCP to RLC, and option 4 actually bisects RLC to MAC. And interestingly, there are also various other options defined, like if you see the option 3, option 5, and option 7 in the picture. So that's again, the bisection happens internal to the layer. So we just split, for example, the MAC into the upper MAC and the lower MAC, phi into an upper phi and the lower phi, high phi and the low phi. So basically, that helps gives the implementer more granularity on what kind of option he want to pick up, considering various trade-offs involved in the the implementation as such, and where he want to keep which part of the protocol stack as such.
That's great.
So, Houman, on that note, can you explain on why most of our customers are speaking about the option 7 as such?
Yeah, if you look at the picture here, Waraj and friends, the option 7 kind of splits the PHY or physical layer. And I don't know if our audience knows that ever since 2013, with introduction of our LTE toolbox, and in 2018 with the 5G toolbox, we are entering the design environment for the cellular technology, meaning that our customers are using our tools to model, simulate, and test primarily the physical layer of the cellular communication networks, both LTE and 5G. And when the ORAN Alliance had that option 7 and multiple versions of option 7, it was natural for us, as we are taking care of the PHY, to be able to adhere to the specifications of ORAN when it comes to the physical layer processing at PHY. As Umaraj mentioned, there is a high PHY and low PHY. I'm going to define that in a second. And that was the motivation for us to zoom in into the functionality of 5G and try to put it in context. So as I mentioned, the 5G toolbox is our tool for simulation, analysis, and testing of 5G wireless communication systems. And what you see here on the left-hand side is a typical end-to-end link level simulation that are enabled by us in MATLAB. So you see here on the top side over the transmitter, the essentially transport blocks from the MAC, the bits that are dedicated in the MAC, come to a downlink processing chain. So what you see here is downlink processing chain. Data comes from the layer 3, layer 2 MAC into the physical layer. And the first thing that happens in 5G is for the user data is downlink shared channel, DLSCH, which essentially is about taking the transport blocks, right, and doing channel coding. Algorithms like LDPC for user data and polar coding for the channel channels that control channels. And then you have a sequence of operations defined by physical downlink shared channel. And that starts from scrambling, modulation mapping, pre-coding, all of that. And then at some point, you take all that data that is modulated and pre-coded, and you compose the time frequency grid, where based on different layers, based on time and frequency, you organize your data into various sections of the resource grid. There's a locations for user data, there's a location for control data, there's a location for signals, and so on. And then you transmit that over, after you do the cyclic prefix-based OFDM, you take the signal and turn the baseband into RF, transmit over the air. There is channel modeling and the inverse operations that we do to recover the best estimate of the transport block bits. So this is the perfect place to introduce the signal flow of the ORAN and the different 7 splits, 7.1, 7.2x, 7.2, and 7.3, and how they relate to those ORU, ODU, and OCU. So take a look at this. You see that the definition of ORU. So ORU, which is the Open Radio Unit, it essentially happens, the split between ORU and ODU happens at the ORAN 7.2x split. Now, when you look at the location of that split, that's after the resource element mapping or resource grid generation, and before the IFFT and cyclic prefix to end up in OFDM symbols. So that is a very good, a very critical point of the ORAN 7.2x specification. So ORU goes from resource grid generation all the way to RF. So it concludes the RF component and what's known as lower PHY. Okay, whereas the distributed unit contains all the elements of the high PHY, meaning all the encoding and channel coding, the LDPC and all that stuff, scrambling, modulation, layer mapping, pre-coding. And these are more essentially computationally expensive part of the PHY, and they are subject to be put in a place where it's convenient to put them on the cloud maybe. So that is the motivation for that split. And then the ODU goes beyond the high PHY, and the MAC and RLC layers, the layer 2 and layer 3, are involved with that. And as Uvaraj mentioned, after that, we go to the mid-haul and the OCU, which is the even higher layer processing. So that is the relationship between ORU, which is the radio unit, which includes RF and low PHY, ODU, which is the computationally extensive unit, which has the high PHY, MAC, and RLC, and OCU, as it pertains to the signal flow of a typical 5G wireless communication PHY processing. All right.
That's interesting. Yeah.
Okay. Now, I want you to do me a favor, Uvaraj. Give me your opinion of that 7.2x is a very important point in this ORAN specification. It kind of splits the PHY in the middle. It's a boundary between ORU and ODU, right? Now, why do you think they chose that resource grid generation, resource element mapping as the location for 7.2 split? Give us a little bit more insight on that.
Yeah, so basically, if you see in the wireless communication system, so the logically split happens between the RU and the DU in 7.x splits, and the closer you get to the ORU, the higher your throughput can be, and therefore all the options of split 7 is applicable, for a logical split, and particularly 7.2x is very important to our customer from the implementation point of view. So, for example, the closer you go to the RU, you'll have a better bandwidth to cover, and the latency, the requirement is well managed, so you get very less latency by keeping the RU lighter, and hence, all the software part of it is pushed to the edge cloud, and RU is able to process the packets faster, and hence the latency reduces. And this paves way for various new applications of 5G, the other applications like the massive mission communications or the ultra reliable low latency communications, which paves way for various new applications like the IoT or connected missions, the connected vehicles, connected factories. So all these new applications need a stringent latency requirement, and this split may help in satisfying those conditions, and hence 5G can pave way for many new applications on that front by removing the bottleneck as such. So these are some of the important reasons. What I think.
So just to clarify, so you're saying that on the screen below the 7.2x split, all those ORU, lo-fi and RF stuff, they can be implemented with lower delay because the major lift in the signal processing happens in hi-fi, right? The encoding especially, and so on and so forth. So And if you have those separation between ODU and ORU, your radio signal, your radio component can be more nimble, more efficient, right? And have less computational complexity, so you can focus on the RF component aspects, right? Whereas the Hi-Fi can focus on the using high throughput devices and so on to reduce the complexity. And by not joining them, by separating them at 7.2x, you provide both of them the chance to be optimized, right? At each level. Yeah.
And maybe how do you think, Houman, to take this to the implementation level, and what are the real environments? What are the real environment components look like, and how is the signal processing done? How is the signal flow looking like, between the RU and the DU?
Yes, I think my next slide can show that. So remember, from top to bottom, you're moving around. On the top of this page, the transport blocks coming from MAC layer, right? And the Hi-Fi takes care of all the complex signal processing. The Low-Fi takes care of the generation of OFDM symbols and RF. At the 7.2x, you have an interface. Now, that's exactly all that stuff that I told you is characterized here by this graph here. In the top part of the plot, you see that the data is coming from OCU and going through RLC and MAC. At the interface with Hi-Fi, all those high complexity signal processing things like channel coding and stuff happens. And then there is that 7.2x interface right there. So at the end of Hi-Fi, or when the Hi-Fi operations are complete, you have access to the resource grid, right? The 5G resource grid. And these are essentially pre-encoded modulated symbols, right? So you have to use compression, decompression to make the bandwidth required to transmit them from the ODU to the ORU reasonable. So there are three components have to be introduced here. You take the resource grid at the end of or at the completion of the Hi-Fi processing, you compress them. Then you take these compressed bits, right, representing the different resource elements, and you capture them into a eCPRI a packet. Now, eCPRI packets are important because that's the very well-defined packets by the standard to let you then put that eCPRI as part of an Ethernet frame and transmit. Okay, so that happens at the end of Hi-Fi to the and the most probably wireline or wireless connectivity between the ODU physical unit and the ORU physical unit. Now, when you receive that packet in the ORU, which is usually associated with the actual base station, you take the Ethernet frame, you take the Ethernet packet, you extract the eCPRI fields, and you do the decompression operation. And you get back the resource grid, and from that you go and perform essentially IFFT and cyclic prefix, which characterize the OFDM modulation, and then map it to different antenna arrays and use the RF processing and take it to RF signal. So that is essentially the implementation aspects of the open front haul. The front haul, which is the interface between the ODU and ORU, needs these three elements in each side: compress, decompress, eCPRI, Ethernet, such that the two parts of the PHY can be successfully separated. Okay.
Right. That's very interesting to know about that.
Now, okay, so we have understood the need for making components and interfaces, ORU, ODU, OC. We understood that the ODU and ORU have a 7.2x split, and between them is open front hall. And we understand that we have to introduce those extra elements for the successful transmission of the hi-fi from the ODU to the lo-fi in the RU. Do we have any implementation of such thing in MATLAB, Uvaraj, that makes this overall design challenge easier to handle?
Yes. So, you know what, using 5G toolbox, we'll be able to easily implement certain aspect of what we discussed in the previous slide. And basically, 5G toolbox can be used to generate the front hall CU, DU plain messages, and for ORAN, especially for the compression and to satisfy the conformance testing part of it. So you get the raw 5G data. All the physical layer functions are available as a part. I mean, for the hi-fi and lo-fi as a part of the 5G toolbox, and the functions are very modular, and you'll be able to pick up all those functions, implement the split, and bisect like which part of the 7.x you want to implement, and then add the interfacing part to the functional split which you are planning to do. So basically, there are various techniques defined by the standard between the DU and RU for making the transmission more efficient. For example, there are bandwidth saving techniques like the compression techniques. So we have various compression techniques like the block floating point compression, mu log compression, block scaling compression, and various other compressions like modulation, beam scaling, beam space, and so on. So you have the functionality implemented in MATLAB 5G toolbox for block floating point compression and mu log compression and the block scaling, and hence you'll be able to do the compression as well on top of the 5G components which you have. So once you're done with the compression using the Ethernet packet closing, so you'll be able to pack that compressed packet into EC3 messages, and then pack that into an Ethernet packet, and then transmit it to the the RU. And in the RU, you'll be able to receive the the Ethernet packet, take off the Ethernet header, go through the the EC3 packet, and then remove the EC3 header, and then you'll get the IQ samples as such. So it's basically the IQ samples in the user plane, and in the control plane, it's basically the control messages. So standard also define various aspects like the energy saving and various other configuration mechanisms and interfaces. So so the couple of other interfaces are like the management interface, which will help in exchanging management messages that can be through an IP based protocol and the netconf protocol. And there is also a synchronizing interface which will help in synchronizing the DU and RU, but we are not focusing on those because those are a bit easy, and that happens when you go real hardware implementation. So when you are in the CU RU work, so the main focus is on understanding the control plane and the user plane data, how to compress it and transmit it to the RU, and how to decompress it and take it forward from there, so that device interoperability can be easily tested. So if you see the picture here, the left hand side one, top one shows how you get the data from the 5G toolbox, compress the message and export it into PCAP, and that can be sent to the RU as such. So C-plane message from various slots can be sent from the DU to RU, and on the right hand side you see a small snippet of the U plane message, which is having an Ethernet packet. with the Ethernet address, and you have ORAN front haul ECPRI based packet, and inside which you see some of the configurations and as well as the PRBs of the resource grid packed into that, and you also see certain the reserved and the exponent bit, so that will be used on the receiver side as well. So this is one of the implementation of the ORAN aspect in the MATLAB environment. So you'll be able to easily generate control and the user plane messages for ORAN fronthaul testing in the MATLAB environment easily.
That's great. So if I am understanding you correctly, so one of the challenges that people have in first implementing and testing these ORAN open front haul interface, for example, they want to make sure that the resource grid that is computed at the end of the physical downlink or physical uplink shared channel processing, the resource grid is adequately compressed, transmitted, and decompressed, so the received resource grid is very similar or close to the resource grid that was transmitted across the interface, right? So having all these different signal processing elements with source code available could be of use, right? Because you know exactly how the LDPC processing is done in encoding. You know exactly how scrambling is done. You can see it line by line, how modulation is done, layer mapping is done, how different layers are mapped, how the pre-coding is done for the user data as well as the reference signals, the modulation reference signals, and how you map that data in different location of time, frequency, and layers, right? So if you know that and you have access to that in source code, MATLAB source code, then when you test the ability to compress packet as ECPRI, which is known as Enhanced Common Public Radio Interface. That's the format, right? And then you load it into an Ethernet packet, you transmit across the interface, front haul, and you decompress and back, you can see line by line how all of these things are done, right? So the task of testing becomes easier because you have access to the source code describing not only the open RAN interface functionality of compression, decompression, ECPRI and stuff, but every possible element of the 5G physical layer, including low-fi and hi-fi, right?
Right.
And all right, with that, I think we have mentioned the major components that we offer in terms of not only modeling the ORAN 7.2, especially 7.2 split and front haul processing, but all the functionality needed to define and test the interface known as open front haul. Is there anything else you want to mention, Uvaraj, as a concluding thoughts before we open the floor to any question anybody may have?
Yeah, so maybe we would recommend everyone in the bridge to post any questions, so that we'll be able to take it up. And as you nicely said and concluded, Houman, on the various interfaces and how that can be easily implemented. So the additional features such as on top of the modular 5G based ready-made functions, the additional interfaces or the support of ECPRI and Ethernet packet creations, encoding and decoding of it, and again the ECPRI encoding and decoding part of it adds value here, in making the ORAN implementation as such easily. So maybe if somebody wants to use it to generate the data to test the RU, so it will be very easy, to generate it as a part of MATLAB and then package that into PCAP and then use that maybe in the receiver side, or again the vice versa, right? Somebody want to get the data from the RU and test it in so that the DU and test it in RU. So the reverse is also possible. So whenever you have a PCAP dump from your DU, so you'll be able to take it inside and then decode it and then see how it works inside the MATLAB.
So as you can see,
so
thank you, Raj. Raj focuses on the practical engineering aspects, like all the tools you need to focus, right, on the task at hand. And I want to also emphasize that because we are committed to standard-based wireless communication, especially mobile wireless communication, majority of the standard-based technologies out there are supported by us in MATLAB. So as I mentioned, we are in the cellular business with the introduction of LTE toolbox in 2013, 14, and 5G toolbox only 3 months after the release 15 of the 5G standard. We had our first version of the 5G. And also we are committed to the ORAN specification because that is something that enables creativity and collaboration, meaning the operators can pick and choose what vendors they choose for different functional components. And as long as the functional component makers write correctly to the interfaces that are defined by the standard, then anybody can work together. And we are doing everything in our power by providing modeling and simulation and testing capabilities to make sure that the builders of the components can easily have a place to verify and test their designs before they actually roll it out. And operators can have an independent test in MATLAB for their design. So if they get functionality from different vendors that make those components, they verify that the vendor gives them something that is according to standards. So that is the role of our MathWorks tools. Enable the equipment maker to verify before they build and sell, and enable the operators to assess performance before they actually commit to a vendor. So that is the value we give here. With that, I want to thank everybody for listening to me and Uvaraj on this lecture part of this talk. And if there are any questions, we would like to engage with you. Any and all questions about ORAN or how it's implemented and how MATLAB can help you with that.
Yeah, thank you all for listening, and we'll be happy to take up your questions later as well.
I see one question. When is this functionality for ORAN introduced in MATLAB? Okay, so the actual release of MATLAB with the ORAN functionality is essentially less than a week ago. It's very new with the release 2022B of MATLAB. So Uvaraj and I will have a full disclosure about the MATLAB functionality for implementing the open front haul and the interface and all the compression and so on soon in October 20th. But yeah, the MATLAB version that contains ORAN functionality is the latest version of MATLAB. And as you know, we release MATLAB twice a year, A release and B release. B release in September, and this release was in September 14 of 2022. So the latest version of MATLAB contains our ORAN functionality.
Houman, we have one more question there. Whether you'll be able to test, implement and test both the transmitter and the receiver side of it. So any comment on the G-Node B and the UE part of it, along with the ORAN as a structure.
So this is that end-to-end link level simulation that I told you about, Uvaraj, right? So if the data comes in a downlink format from the higher layers as transport blocks, we have all the functionality to go to do the hi-fi. Yes, and that's the channel coding, all that stuff that is high computational complexity. Then you end up at the resource grid, and then we do all the compression and decompression and all that packet stuff, and we have the modeling of what arrives at the ORU as the resource grid. Then we do the RF, the OFDM modulation and RF transmission aspects, channel modeling, and then we do the essentially as the signal is received to the UE, we do the receiver operation on the UE to get the best bits and communicate. And then in our 5G toolbox, we also have the other version, the uplink, where the data is transmitted from UEs, arrives at the base station, and first the, RF operations and the low-fi are performed, and then same operations, same compression, decompression, and characterization, all the way to decoding at the base station, the data sent from UE. So both directions, downlink and uplink, we have the capability of including the ORAN, open front haul, 7-2X split operations in the end-to-end simulation.
Okay. Okay. Yeah, that's there's another follow-up question on the same line. Like, can I export and import downlink and uplink PCAP files?
Yes. So this is one of those things that most people don't know about. PCAP is a packet capture file format, right? It's a standard file format, and all the downstream tools like Wireshark and so on, if you write and read if you write into a PCAP file format, they can show you exactly how the packets and how the bit allocations and how the fields and stuff will look like. So we have already developed in MATLAB a PCAP file writer and a PCAP file reader. So let's say you go and research at the resource grid, you have the data, you compress it, you put it in ECPRI format, and you write it into a PCAP file format. And that PCAP file format can be opened up by any software outside MATLAB, right? And you can take a look at it. And then if you have any software outside MATLAB contains the Ethernet ECPRI data in a PCAP file, then MATLAB can read it and continue the operation. Right. So you don't have to have all the operations happen in MATLAB environment. You can use the PCAP as the file format to split the operations between different environments.
You also have one more question. If we have a running 5G network, can we install ORAN on it? Maybe I can take that. Yeah.
Well, so it depends what the running ORAN on it means. I'm sure if you look at the different components, you can find the split and do that. Go ahead. What is your impression of the question?
Yeah. So the question is like looks like it had asked he have a running 5G network with him. So maybe we need to understand further on, how the 5G network is implemented. Is it simulation environment or is it a real-time implementation? And then, we just want to understand again, what component of ORAN you are planning to implement. So is it a traditional 5G network or an ORAN-based 5G network which you are running? And, so depending on that, we'll be able to take a call on that. Maybe you can drop us an email and we can understand your query better. And
Yeah, you can engage us at the email you see on the bottom of your screen and talk to us there. Also remember that what we showed you was the ORAN architecture followed by ORAN signal flow and data processing, signal processing aspect, and the availability of MATLAB to do that. Then there is another layer is actually implementing all that stuff into either FPGAs or ASICs or ARM processor, which is a lower level implementation. And we haven't discussed that part because that is left for our webinar next time. But that's for different levels. You can use the ORAN specification in 5G Toolbox as a reference for even low-level implementation in C, C++, very ROG, VHDL, and so on. And for that, we can use that as a reference. Yes.
Another important question and interesting question, can you implement ORAN on commercial SDRs, software-defined radios? Maybe I can take up that question. So, yes, you'd be able to implement, for example, if you have your DU in a software environment, and if you want to test your RU in a hardware, right? So you'll be able to, create the IPs for, the lower phi part of it and put it in the hardware. Use your SDRs for, for transmission, real-time transmission purpose. So we have a customer, who have done exactly the same thing, implemented ORAN on FPGA and, for testing the user equipment as such. So maybe I'll put the link for the user story in the chat window. You can have a look. So that will be more relevant to what you.
Just remember, so the ORU is the lower complexity part, right? So some of our customers take the hi-fi, right, and implement all the way to resource grid generation aspects, and then they capture that PCAP file, the EC3 packets, and as they take that, they use that to generate from that the rest of the lo-fi operations and then transmit over the air. That is the approach that, and as long as your IFFT and cyclic prefix, all of that is implemented on FPGA, you can take the data, decompress it, go through the OFDM modulation on the actual hardware, and then transmit on the antennas. So that is one way to test the communication when the PCAP packets that contain the compressed resource grid can then be transmitted over the air when all the thing that the RF instrument or the SDR does is take the resource grid packet and just the OFDM modulation, RF circuitry transmit. So that is something that a lot of customers are asking us to do. Yeah.
That's actually a very interesting use case, designing, the system and then taking it into over-the-air kind of simulation, and it's a real-time simulation, right? So
yes.
That's a very interesting use case, starting from design, development, and to the production.
And doing it in pieces, Uvaraj, right? The OFDM is the not as complex as LDPC, which is in hi-fi, right? So if you put the OFDM on that operation on the chip of your SDR or RF instrument, and you get all the hi-fi stuff through a PCAP file into your, to your wire connectivity, you can test at least the OFDM and a different kind of bandwidth, different kind of carrier frequencies. So that way, you don't have to put in the limited resources of your SDR RF instrument all the 5G,
Right.
downlink processing, only the OFDM part. And then you can get the ODU part through ECP packets to the SDR RF instrument and test. So that is an application that I think our customers have told us about numerous times.
Yeah. And that makes life easy as well, right? Implementation in FPGA is quite complex. So we keep the lesser implementation in FPGA, and we move the complex part, to the signal processing part into higher efficient edge cloud, so that that's taking care of the computation aspects of it.
That's it. Great questions, Waraj. Is there anything you see, guys, on the note?
So that's all the questions I see. Maybe we can, our email IDs are displayed in the screen. So if you have further questions, please drop us an email. We'll be happy to take it offline as well and support you.
Yeah, let me just go beyond that a little bit, Uvaraj. So you can contact us, Houman Zarrinkoub and Uvaraj Natarajan, anytime you want using our email you see on the screen. You can always contact us at webinars@mathworks.com, and our team will, if you don't remember our exact name, just use webinars@mathworks.com, mention this YouTube, and they will find us. And you can go to our products, and there is a chance for you to contact us through our products, 5G Toolbox, LTE Toolbox, other toolboxes. There is a place to contact the product manager, which happens to be me. Yes, it's a pleasure to be with you today. I think we have managed to get an overview for you of what ORAN is all about, how it's implemented, how it's tested, and we look forward to further communication with you. Remember, I think our friends in our YouTube experts have communicated with you the date and time of our next webinar, which goes through more detailed implementation aspects of ORAN in MATLAB. And that webinar is scheduled for October 20th. And we will communicate with you the different other collaterals we are building. Uvaraj is writing a paper on that. I am writing a discovery page. And we will get you those material if you're interested, if you contact us through our regular channels. All right. Thank you very much on my part. I hope you have a wonderful rest of the day.
Thank you very much, everyone.